Our model now will have two network outputs to train. The Y encoder mean, which corresponds to our previous encoder, and the Y encoder standard deviation, which just produces the currently allowable standard deviation for each mean output during the training process. Since now our loss function consists of two components, we combine them in the training loop using a Lagrange multiplier to combine them in an overall loss value. And you can read more about the Lagrange multiplier here. Basically, the Lagrange multiplier simply weights the two components to achieve a desired trade-off between them. In our case, it will look like this. So we will have our mean squared error loss plus the variational loss with a factor of 0.01 in our case, and this is our Lagrange multiplier. Here we also see that we can choose between two mentioned variational losses. So we have the variational loss and also the variational loss 2, that is the mean squared distance from above, and the standard variational autoencoder loss. In our experiments, the program will read in two speech files as a simple training set. It is read in such a way that each file is one batch, and we use the signal to pytorch function to convert our arrays into pytorch tensors. Here we can define the actual autoencoder. So we have here the analysis filter bank for the mean values, and then for the standard deviation values, and then the synthesis filter bank. So we have here self conv1 mean, and we will use 32 output channels, kernel size of 8 times 2048, and the stride of 8 times 1024. For the standard deviation values, we use the same characteristics, so it's 32 channels, 8 times 2048 for the kernel size, and 8 times 1024 for the stride. This will be this convolutional layer for the standard deviation values. Then we have the synthesis filter bank, and we are using the convolutional transpose 1D. Then we have our encoder mean. We are also using the tanh as activation functions. So remember that our values will be from -1 to 1. Then we have the encoder standard deviation, and in this case we are having an absolute value together with the tanh, so now we will only have positive values. This is for the analysis. Then we have the decoder, and we have our forward method, and here we see that we also have this part here where we are adding the Y encoder mean plus the Y encoder standard deviation, and we are multiplying by this torch rand and like function, and we are going to talk about this later. Observe that the autoencoder uses filter kernel sizes of 8 times 2048 and strides of 8 times 1024, but we only use 32 channels, and this means that we have a very tight bottleneck here. The factor 8 here is just for experimentation, and you can replace it by 1, for example. Then we would have shorter filters, shorter strides, and the bottleneck becomes less tight, but the results will be much more noisy. And in addition to our previous encoder, which here we call the conv1 mean, there is also the encoder for the standard deviation of the added noise in the encoded domain that we're calling conv1 std. Like I explained here before, we have the conv1 mean and the conv1 here std is the torch rand and like, and it returns a tensor with the same size std as input that is filled with random numbers from a normal distribution with zero mean and unit variance, and this is what we are using here for this Y variational. So now we'll go through the full code for the variations. We autoencode my matplotlib pyplot. We are importing our pytorch. And we can also use the scipy.io WAV file to read in audio files, and we are also going to use librosa if we will use MP3 files. Here is the function signal to pytorch that converts a signal vector, for example, like a mono audio signal, into a 3D tensor. Here is the definition of our model, the conv autoenc that we talked earlier, and we have our encoder mean, our encoder standard deviation, our decoder, our forward, and here we have our loss functions. So we are going to experiment with two different loss functions. So we have our variational loss that returns the variational loss from arguments mean and standard deviation, and you can see it from the paper autoencoding variational base. That was the equation that we talked before, but also we can have an alternative that is the mean square distance from the ideal, mu equals to 0 and sigma equals to 1, that is given here. So here we are preparing our training set. So we're going to use the famous speech from the introduction of Iron Maiden, The Number of the Beast, and also the speech from Iron Maiden, Ace is High. So we're just preparing here. Will be the batch 0 is one file, batch 1 is the other file. We do some normalization, we convert to PyTorch tensors, we generate our model, and we define the loss function, the part that is the mean squared error. And then we are here. So we have this part ready. Here we are defining also our optimizer. So we are using the Adam optimizer with a learning rate of 1e to the power of minus 4. And then we can start our experiments.